Hello everyone, welcome to this presentation. In this video, I'm going to show how to obtain the frequency response of a power converter. Particularly, we are going to see the frequency response of a buck converter. Okay, so firstly, we are going to see the buck converter under study. Then we will see the process to obtain the frequency response, how to implement this process in LTspice, and finally an example. I have to say that this process of obtaining the frequency response of a power converter has been obtained from these references, this reference entitled LTspice, Basic Steps in Generating a Boat Plot of Switch Mode Power Supply by Gabino Alonso, that you can find in this link here below. Having said that, we are going to study our DC-DC buck converter, and this is the topology that I have selected as an example. We have 10 volts at the input, and we are going to generate 5 volts at the output. Okay, the inductance has a value of 50 microhenries, capacitance is 10 microfarads. We have the diode. The series resistance of the inductance is around 50 milliohms, and the series resistance of the capacitor is 150 milliohms, and our resistance load is 1 ohm. So we are going to obtain 5 amperes through the load with a power of around 25 watts. So we know that the buck converter behaves like second order circuit with a second order frequency response. We are going to consider only the buck converter operating in continuous conduction mode. So we know that the response of our converter is going to be like this. We have, and this would be the plant. We are controlling the duty cycle of our switch using this signal, the duty. Okay, comparing this signal with a ramp, then we are going to generate the duty cycle, the PWM waveform to control the switch. Okay, so we know that the response of this PWM modulator can be approximated like 1 over BPP, sorry, being BPP and the peak-to-peak voltage of the ramp. Okay, so this is usually the model for the PWM modulator. Then we have our buck converter that is going to behave like a second order circuit. Okay, so we are controlling the duty cycle D and generating the value of the output voltage VO. So we know that the response of the buck converter in continuous conduction mode is like this. The gain is equal to VO divided by D and divided also by BPP in this case. So in our converter, this is going to be something like in decibels, something like 0 dBs. Okay, 5 over 10 divided by also 0.5. Okay, BPP is going to be 10, and the duty cycle in order to obtain 5 volts is going to be around 0.5. Okay, so this gives us 0 dBs. Then we have a double pole at the frequency Fp, which is given by this expression, because at the end the inductor and the capacitor behave like a resonance circuit. So we have this double pole here at this frequency, 1 over 2 pi, also times the square root of LC. Okay, and this in this case gives 7.1 kilohertz. And then we know that we have a 0 in our response, which is given by the series equivalent resistance of the capacitor. Okay, and this 0 is at a frequency F6, which is this one, 1 over 2 pi C times the series resistance of the capacitor. And with these values, we have this frequency of 106.1 kilohertz. Okay, so this is the frequency response that we have to expect for our converter. Okay, a pole here and then a zero here. So we have this slope, okay, minus 40 dBs per decade here, and then this other slope here, minus 20 decibels dBs per decade after or beyond the zero. And the phase is going to be 0 at the beginning, and then it will go to minus 180, but then it is going to increase again because of the effect of the 0, ideally ending in minus 90 degrees. Okay, so our objective is to obtain this frequency response using LTspice. So now let's check the operation of this converter, obtaining a transient simulation of the converter, of the buck converter. Okay, for this I have ready this file here. So we have the input voltage, okay, the transistor, diode, and the inductance, the capacitor, and the load at the output with 1 ohm. Okay, and in order to generate the gate voltage here, we are comparing the constant value of the duty cycle, our signal V duty, compared with a ramp, okay, generated like this. We are going to operate at 200 kilohertz frequency, okay, so the period is 5 microseconds, and the duty cycle is going to be a little bit higher than 0.5, 0.54 in this case, in order to compensate for the losses in the different elements and get 5 volts at the output. Okay, and then we are going to do a simulation, a transient simulation up to 500 microhenries, okay, with a step of 0.1 microsecond, sorry. So you can see that we are using this comparator that we have developed in the last video on the in the LTspice series, okay. So with this ideal comparator, we generate here the signal in the PWM waveform, and we are sending this waveform to this behavioral source, voltage source here. So we have here exactly the same waveform applied to the gate with the gate resistance to limit the current through the gate. Okay. So now we are going to start the simulation and see some of the results. Okay. So we can see here, for example, how the modulator is operating. We can see the sawtooth waveform here. Okay. So it will be like this. And then we have the duty cycle signal. Okay, it's a constant value. Okay, and then we can see the PWM waveform. Okay, so if we do a zoom here, we can see better the different waveforms. We have the sawtooth waveform in red, then comparing it in blue with the signal V duty in blue, and then we get the square waveform that is going to be applied to the gate with a maximum value of 15 volts. Okay, so we can see now the output voltage. For example, I'm going to add a new plot pane here, and then let's see, for example, the output voltage. Okay, this will be around 5 volts. Okay, we can see the complete simulation if we do, sorry, here the complete zoom. Okay, so we can see how the output voltage is increasing until reaching approximately 5 volts. Okay, and we can also see, if we like, we can add another plot paint and see, for example, the current through the inductor. Okay, we can delete now this paint to see this better. Okay, so we can see also the current through the inductor. Okay, so with this we can see that everything is working fine in our converter in this transient simulation, and now we can go ahead and obtain the frequency response of this converter. So how to obtain the frequency response of a converter, or in general of any system? Okay, I'm going to explain this using this slide here. The frequency response of any system, in order to obtain this frequency response, what we are doing is to inject a sinusoidal input superposed to the DC operating point. Okay, like this one here, we have our V duty, which is used to control the output voltage. Okay, and then superposing to the DC value, we add a sinusoidal waveform, a modulating sinusoidal waveform with a small amplitude. Okay, we are going to name this like VD. Okay, here, and this would be in the modulating frequency. Okay, so when we inject this signal, what we are going to have at the output is again also the same perturbation with the same frequency and with a given amplitude. Okay, so we are going to name this VO. VO is just the AC component at the same frequency of the modulating frequency. Okay. Of course, in our system, we are going to see also the high frequency ripple superposed to the output voltage, but we are interested only on the peak-to-peak value of the AC signal at the output, with the same frequency as the modulating frequency at the input. Okay. So with these two signals, we can obtain the gain of our frequency response by dividing the amplitude at the output by the amplitude at the input. Okay, the peak-to-peak amplitude here, okay, will be this magnitude here, and the peak-to-peak value at the input could give this other magnitude, and then by dividing them we can obtain the gain, and then the gain in decibels by using 20 times the logarithm of this magnitude. So the phase of our response is just a matter of comparing the phases of the output signal compared with the phase of the input signal, and then do the difference. Okay, and then we can do this for different frequencies. Okay, and then obtain the different values of the gain and the phase. Okay, and then we can do the representation, okay, at the different frequencies. Okay, so this is the idea, so we can obtain our both diagram for both the gain and the phase. Now we are going to see an example of how to do this in LTspice manually, okay, to better understand this process. So for this, we are going to use this other file in LTspice, in which I have only added this sinusoidal voltage superposed to the duty cycle here. Okay, so with this we are injecting, or we can inject, a sinusoidal waveform superposed to the DC value in order to modulate the duty cycle and see the modulated signal at the output. Okay, so in this case, I'm going to add a sinusoidal waveform at 1 kilohertz and with an amplitude of 2 volts. Okay, so in total is 4 volts peak to peak. Okay, we're going to see this. Okay, I'm going to run the simulation. So first we are going to see the modulation of the duty cycle. We can see here the waveform here at the input. So we are injecting the 5.4 this 5.4 volts voltage here, okay, with an amplitude, okay, superposed sinusoidal voltage superposed to it with an amplitude of 2 volts or 4 volts peak to peak. And then the sawtooth waveform, okay, here, okay, of course, a much higher frequency, okay, so we can see also maybe in another pane, we can see here the duty cycle, which is going to be modulated. Let's do a zoom here. Okay, so we can see that here we have higher value of the duty cycle, and here the value of the duty cycle is lower. Okay, so we are modulating the duty cycle. Let's see now how is the output. Okay, we are going to delete this one and see here the value at the output. We are going to do a zoom, sorry, full here, and then we can see how the output voltage, okay, has the average value of 5 volts, and then a modulating voltage, okay, at the output. So we can delete now the sawtooth waveform. So this is the modulating signal at the input, and this is the modulated at the output. Okay, so by comparing these two signals, the peak-to-peak values and the phase of these two signals, then we can obtain the gain and the phase. Okay, but this will be quite painfully to do it manually. Okay. You can see that they have different amplitudes and different phases. So we could calculate the peak-to-peak value and so on, okay? But this will be very difficult to do, okay? But we could do this if we increase the frequency, and let's say, for example, 10 kilohertz, then run the simulation again, and then we could obtain again the another point for our bow diagram. Okay, we can go to further frequencies, for example 50 kilohertz. Okay, let's do a zoom here so we can compare here the input voltage and then the output voltage in green. Now we can see that the amplitude of the AC signal at the output is very small because we are injecting higher frequencies, so the gain is lower. But maybe we can see it in another pane separately. Going to this other pane, we can see that we have this component at 50 kilohertz, but now we have other components because we are approaching the switching frequency. Okay, so the modulating frequency is close to the switching frequency, so we have interaction between them. Okay, even if we go to 100 kilohertz, which is half of the switching frequency, okay, we can see that now it is much difficult to obtain or to distinguish the modulating frequency and the switching frequency. Okay, so we cannot expect very good accuracy when obtaining the frequency response and the Bow diagram when we are approaching the switching frequency. Okay. Also because when we are modulating our duty cycle at a frequency close to the switching frequency, it does not make much sense because Now, as you can see, both frequencies are very similar. Okay, so all the methodology of averaging circuits to modeling is not valid when we are approaching the switching frequency, okay? Because we are operating very far from the linear behavior of our model. Okay, to modulate this, we will need probably non-linear models. Okay, imagine that we use, for example, now 200 kilohertz, which is exactly the same as the switching frequency. Okay, then it does not make much sense to inject a modulating signal which is at a frequency similar to the switching frequency or even beyond the switching frequency. If we go beyond the switching frequency, say for example 400 kilohertz, then we can see that there are going to be different switching. So if we let's delete this one, show here the value of the duty cycle, then we can see that we have different values. So we are not modulating the duty cycle at low frequency. The question here is how to measure accurately the peak-to-peak amplitude at the output and also the phase at the output of the AC signal and the output. Okay, we could do this point by point using the cursors and so on, but this will be painfully and it will take a lot of time. Okay, so what is the solution to implement this quickly? The idea is to use the Fourier transform to obtain both the amplitude and the phase of the harmonics, of the different harmonics, because we need to obtain the amplitude and phase of the output harmonic, but only at the modulating frequency to be compared with the AC signal at the input. Okay, so for this we use the Fourier transform. Okay, and then we applied these well-known expressions here in order to obtain the real part of the harmonic and the imaginary part of the harmonic. Okay, so this is just the expression, the Fourier mathematical expression. Okay, using the integral of our signal. This could be the output signal. Okay, and then the real part of the harmonic is 2 times 1 over the period of the modulating signal and the integral of our waveform under study times cosine of 2 pi over the modulating period time. Okay, so how to do this integral in LTspice? Okay, we can do this integral in LTspice using this mathematical function, the average function. Okay, so we can just do 2 times the average value of our waveform, okay, under study, times cosine of 2 pi divided by tmt. Okay, so this is just as simple as this. We can do the same with the imaginary part of the harmonic. So it will be the same integral, but using the sinusoidal function here, and then doing the integral using the average function. Okay. Once we have the real part and the imaginary part, it is very easy to obtain the amplitude and also the phase. Okay, excuse me. So remember that the amplitude is just the square root of the addition of the two parts, real part and imaginary part, squared. Okay, and we can implement this function directly in LTspice using the hypotenuse function. Okay, so the hypot function we can obtain with it this value, and then in order to obtain the phase of the harmonic, then we have to implement this function. Okay, is the inverse of the tangent of the imaginary part divided by the real part. We can use this function also in LTspice, the attempt2 function with the imaginary and the real part. And it is better to use this function attempt2 because this function is already considering the position of the coordinates in the different quadrants. Okay, so we don't have to worry about the angle. It is going to provide the correct angle in all the situations. Okay, so let's see now how to implement this methodology into our circuit in LTspice. Okay, for this I have this file here, and you can see that it can be more complicated to obtain the frequency response and the Bode diagram in LTspice than in other simulators, in other programs, but the advantage here is that we have full control of what we want to do, okay, and full control of what we are doing, and this in reality, this gives us much better insight of what we are doing, and we can also understand better how the frequency analyzers in the laboratory operate, or even we can replicate this if we don't have a frequency analyzer in our laboratory. We can replicate this by taking measurements with our scope, saving the data into a file, and then process this file with a mathematical program like WinPython. We could obtain this frequency response in the same manner. Okay, so in this case, what we are doing again is to inject the sinusoidal waveform here superposed to the duty cycle waveform in order to inject our modulating signal. Okay, we are going to use 1 volt amplitude, and then we use here the frequency as parameter because we are going to change this frequency in order to change the different modulating frequencies and do the sweep. Do the complete sweep for the frequency response. Okay, so this is the first idea. Then we are going to do a step analysis in the frequency. So we are going to do different simulations for different values of the modulating frequency, and we do this using this command here. Okay, dot step. We are going to do in decades. Okay, the param is the frequency from 100 Hertz to 200 kilohertz. Okay, and using 10 points per decade. So at each of these frequencies, we are going to do a transient simulation using this directive here, this instruction dot tran from 0 to this time. Okay, this time is to t0 plus 5 times the modulating period. Okay, and t0 is defined as 1 millisecond. Okay, because this is the time that we need to reach steady state. Okay, so we are sure that in 1 millisecond we are going to reach steady state, and then we are going to save the waveforms, all the waveforms from this 0 time, 1 millisecond, plus 5 periods of the modulating frequency. Okay. So then, once we finish all the simulation, we are going to process all the information with these directives here, which are intended to calculate all these values, the real part, the imaginary part, and then the amplitude and the phase. Okay, so let's take a look to this. We use this measure to measure the average value at the output. Okay, A is going to represent the values at the outputs and B the values at the input. Okay, so first of all, we obtain the average values in order to separate the AC component from the DC component. Okay, so the average value of V out and also the same, the average value of V in. Then the real part and the imaginary parts of the output harmonic are calculated like this. Okay, we obtain only the AC component and the output by doing this difference, B out minus the average, and then multiply by the cosine function, and then do the average expression in order to obtain the real part of the harmonic. Same with the imaginary part of the harmonic at the output. We do exactly the same for the real part and the imaginary part of the input, okay, at the input. Then calculate the magnitude at the output, okay, using the hypot expression, then the magnitude at the input, then the phase at the output, the phase at the input, as we have seen using the 8 and 2 expression, and then finally with the well-known expression we calculate the gain magnitude in decibels, okay, and then the phase of the gain. Okay, here we have to do a correction. We have to do the phase at the input minus the phase at the output, okay, because we know that the phase is going to be 0 and then decreasing, so we want to have a negative phase in our representation, so we need to do it like this. Okay, and then these other directives are just to save only V out and V in order to save space and memory. This option here is to use double precision for the data, and then option no march is just to do not plot the waveforms online with the simulation. Okay, so this is our circuit. So let's now to run our simulation and see the results. Okay, so click here, run. You can see that here below in this line, we can see that is running 1/34 simulations. So we need to perform in total 34 simulations to see all the results, okay? Because we need to do several simulations with the different frequencies from 100 kilohertz, from 100 hertz to 200 kilohertz with 10 frequencies per decade. So in total is 34 simulations. Okay, this is to see the Bode diagram with better accuracy. Of course, if we want, we can use a lower number of points, and then the simulation is going to be shorter. Okay. Usually when we are doing our first simulation, we use less number of points to see that everything is working well, and then in order to obtain the final simulation, the final results, then we increase this, and then we can wait a longer time because we know that the result is going to be correct. So now the simulation has finished now, so we can see, for example, here the output voltage if we like to see what happens. Okay, so we can see here many different waveforms, each one for each modulating frequency. Okay, so in red, for example, which is the longest one, is for 100 hertz. Okay, the next one is for the next modulating frequency, and so on. Okay. So we can see here the different waveforms, okay? But this is not what we need to do to obtain our frequency response. What we need is to go to the file with the results, with all the results in text, okay? So for this, we go to this file, okay, by clicking or pressing on the keyboard the key control and then the letter L, okay, as in LTspice, L, and then we can see here the results. Okay, so first we can see, for example, the different frequencies at we are going to inject our perturbation at the input, okay, from 100 Hz to 200 kilohertz approximately, and this will be the different values of the frequencies when we are doing this kind of sweeping. Okay, then we can see the average value at the output, okay, which is something like 5 volts. Then the average value at the input, which is what we are injecting to obtain 5 volts at the output, it was something like 5.4 volts. Okay, then here the real part of the different harmonics. Okay, the real value, the real part of the different harmonics. Then the imaginary part of the different harmonics at the output. Okay, same thing at the input, the real part of the harmonics, the imaginary part of the harmonics. Okay, and then now we calculate the the magnitude of at the output. Okay, so you can see that it is decreasing. The magnitude at the input, of course, we are injecting a sinusoidal waveform of 1 volt, so it is going to be 1 volt. We could have skipped this calculation, but we are doing it anyway. Then the phase at the output, okay, A5, okay. Then the phase at the input, okay, B5, and then the magnitude of the gain, okay, using this expression, and then the phase of the gain. Okay, so with this we have all the data. Okay, but LTspice can also represent this by doing the plotting, and for this we just have to click on the right button of our mouse and then select this plot step measured data. Okay, this is asking that our file has real data and complex data, and then it is asking if we want to write this as complex data. Okay, in this case we answer yes here. Okay, and then we enter in our representation, or we can select here with right click, add traces, and then select the different elements, but in this case we are interested in the gain, and with this we are going to obtain both the gain amplitude and also the gain phase. Okay, so we can see here the result. Okay, so we can see that the gain is 0 decibels. Okay, the gain is here in red in continuous line, and the phase in this continuous line also here in red. So the phase is also 0 degrees. Okay, we can use the cursor if we like to see it better, the different values. So we can see here that at low frequency 100 Hz we have almost a magnitude of 0 dBs and phase 0 dBs. Okay, approximately. Okay, then we can obtain, if we remember here, we can obtain the frequency of this pole, of the main pole here, by looking the frequency at which we obtain minus 90 degrees. Okay, so we can go here and look for the point of minus 90 degrees. Okay, and then we can see that the frequency is 7.47. Okay, which is something very similar, 7.1 kilohertz Okay, very similar to the frequency here. Okay, so we can see also how the gain is decreasing, and also the frequency, the phase is also decreasing, but at a point around here, the phase is again increasing. Okay, due to the effect of the zero. Okay, and of course in this part here we can see that we have some noise and some wrong data, okay, because we are approaching the switching frequency, and then we cannot expect good accuracy when doing this kind of measurement, even in simulation or even in our laboratory using a frequency analyzer. Well, this is all in this presentation. I hope that you have found this presentation interesting for your future activities. Let me know if you have any comment. Thank you very much for watching this video, and see you in the next one.